Hello, everyone. So the talk will be about covariant quantum error correcting codes via reference frames. And this is joint work with Yuxiang, Joe Renes, and myself, Mischa Woods, from ETH Zurich in Switzerland, and Yinmo and Giulio Chiribella from the University of Hong Kong. Okay, so the outline is as follows. We'll start with an introduction, which introduces transversal gates and the Easton-Canil theorem and how to field-convent the Easton-Canil theorem. We will then talk about the results of this paper, where we will introduce our particular encoder and decoder, the error models, a characterization of the decoder errors, and the implementation complexity of our scheme for quantum error correction. We will finish with the usual conclusion and open questions. Okay, so we'll start with the very, very basic. So what is a quantum error correcting code? Well, the basic idea is that we have this abstract space called the logical space, which is where people design, say, quantum algorithms, maybe on pen and paper, right? Have the zeros and ones associated with some logical space. But then if you speak to any experimentalists, they have to implement this in some kind of physical system. So what we have is a so-called encoder, which maps our abstract logical space to the physical space. And in particular, it maps it to a subspace of the physical space known as the code space. And this is important because in any physical system, errors can occur, and they'll take us out of this subspace into the larger physical space, okay? And then the idea of a quantum error correcting code is that hopefully we'll have a decoder which not only can decode the encoded information via the encoding map, but it can also correct for any errors which may have occurred. So in summary, what we should, a quantum error correcting code is a set of maps, an encoding map, error channel, and decoding channel, which satisfy this relationship here. So for any logical state, we can encode it, errors can occur, and we can decode it right back to the logical space, and this should occur for all states in the logical space. Okay, so now let's introduce this notion of local errors and transversal gates. So imagine here I'm depicting a bunch of physical qubits, and one basic notion idea is that we can group these qubits into what are known as a code block. So here I've drawn 3 examples of code blocks, which is just a partition of these qubits. And here, local errors can occur. For example, this is a local error, local error, local error. And when I mean local with respect to the code block. So an error on 1 qubit in each code block. So here, this is an error over 3 qubits. I correlated error over 3 qubits. But within each code block, it's only local. It only occurs on one qubit. So there are models for quantum error correcting where these are easily correctable, these types of errors. So no problems there. And this will be an example of errors which are not correctable within these models. So here we have 2 errors over, or correlated errors over 2 qubits within 1 code block. So this will not be correctable. Here again, we have multiple errors within each code block, multiple errors within code block, multiple errors within one code block. So within these type of models, these types of errors are not correctable. Now, within this setting, we also have a notion of transversal gates, and the point of this is as follows. So clearly, the actual while the individual errors which may occur, in principle, you could imagine them being local, right? Which maybe just happening locally in one qubit. This is if the noise only acts locally. But what you won't be able to avoid is the fact that when you apply your algorithm, the unitaries will have to interact with multiple qubits, right? There's no way of just applying all your gates to individual qubits. They have to, the qubits have to talk to each other, so to speak, right? But of course, that can also introduce errors if you're not careful, or propagate errors, right? If you have a local error. So the idea of transversal gates is they're a set of gates which run transversally to the code blocks. So each unitary in the gate will act on multiple qubits, as I said before, which is necessary in general at least. But within each code block, it will only be local, so only up to 1 qubit. So this is an example of local transversal gates. And why this is important? Well, imagine you have an error on when you implement one of these gates, right? Like so there was a mistake when you implemented this unitary, there was a mistake when you implemented this unitary, or it was acting on a unitary on a local error and spreaded it. Either way, you result in errors of this form. And at least within this protocol, one can easily correct these types of errors, right? Due to the reasons I said previously. So of course, then an interesting question is how many of these transversal gates can we have? For example, can we do universal computation with them, for example, right? And in terms of the maths, we can think of these universal gates, transversal gates that have the following properties that we can. Yeah, if it's a transversal gate, you'll have this covariance in the tree. So we can apply the transversal gate at the logical level, followed by encoding, and that should be the same as first encoding and then applying these transversal gates. And again, it has this tensor product property here, as you saw in the previous slide, to indicate that it apps where these tensor product are transversal to the code blocks. Okay, so how many can we have? Well, as I said, this is an important question, and Easton Keneal answered this in the general case in a POL from 2009, and then no-go theorem here rephrased and simplified is as follows. So if you have two assumptions, namely one, that the code space is finite dimensional, and second, that we can correct local detectable errors, then 1 and 2 imply that the transversal gates which are permissible cannot form a continuous set, nor a universal set, right? And universal in the sense of allowing one to perform universal quantum computation. Okay, so how do people get around these? Well, I will state some approaches. So the standard approach, or one of the most popular approaches, is as follows. So we have one of the gates in the universal gate set is not transversal. So for example, you could apply Clifford gate, which can be implemented transversally, but these are not universal. We have to apply one more gate called the T gate to make it a universal set, and this gate is the non-transversal gate. So here the circumvention of the Easton Keneal theorem, I think, is quite obvious. Not all of the transversal gates form, or I should say, the transversal gates do not form a universal set, right? Another approach is, and I concentrate on this one here because this is the relevant thing for this talk, is the so-called via reference frame approach. So the first paper on this was in 2017, and here they use idealized reference frames. So these are like infinite dimensional reference frames. And here the violation of the Easton Keneal theorem is the first thing. So the code space is infinite dimensional space, not finite dimensional. If you remember on the previous slide, I said that was one of the two possible assumptions, right? Assumption number one, that it has to be finite dimensional. So that's how they circumvent it. Then in 2019 with Alhambra, we use finite reference frames. And here the circumvention is different because now you have a finite dimensional code space. And the circumvention is that we now have an error in the decoding, so we cannot decode perfectly, right? Because in the standard Yuxiang theorem, it assumes that you can do perfect decoding. So here there's an inherent fundamental error in the decoding, regardless of what noise you actually have. And also at the same time, in 2019, Philip Weiss and co-authors also had a method to circumvent the Yuxiang theorem, which again had a finite dimensional code space. So the field convention is the same reason as here, but rather than using reference frames, they have inherent symmetry in the systems that they studied. But the nice thing about this approach is that the error scalings and things is similar to in this approach. So they're also complementary to each other. Okay, let us now look at the model that we will consider. So first off, we start with a subroutine encoder and decoder pair, and our encoding works as follows. So we start off at the logical level with one qubit, and then we draw a unitary at random from the Haar measure of SUD. We apply the inverse of that to the logical level. We apply the subroutine encoding over this to encode to NP physical qubits, or qubits, I should say. And then we apply this unitary that we picked at random over all of the qubits at the physical level. Now here's where the reference frames come in. We add 2m qubits for one reference frame. We apply this unitary that we picked on random on half of those, and then we repeat. We get another reference frame. We apply the unitary on half of them. We get another reference frame of 2m qubits, and we apply the unitary on half of those, etc., until we have enough, until we have nr qubits in total to form our reference frames. Okay. And now I draw this with a slight haze over it because remember, we picked the unitary at random, so there's some randomness to all of this, right? And the actual encoding channel, when you do that, is given by here, by this expression here, where this du is the Haar measure. Okay. And this is now naturally covariant, has this nice covariant property that I was mentioning before, since for n unitary belonging to SUD, if we apply it at the logical level, then this is equivalent or equal to applying it locally at the physical level, right? Or on the physical qubits and also the reference frame qubits, right? So it has this nice symmetry property that I mentioned earlier, and this follows actually from the invariance property of the Haar measure. So it has this nice invariance property here. Okay, so what about the decoding? So here, the first step is to measure the reference frames, as indicated here. And what that does is it basically converts this state, which is what we have after applying encoding, to approximately speaking this state here, where this is the integrand or one particular value of the integrand evaluated at the corresponding outcome of the measurement. Okay, so the measurement, when we measure a quantum reference frame, what it tells us is it tries to estimate which unknown unitary was applied to it, right? And it gives us the answer to which unitary from SUD was applied. So that's what's going on here. And again, I say this is not exact, it's approximate because these reference frames are finite dimensional, and therefore we introduce a bit of randomness. And this actually is the source of the fact that the decoding is not perfect, and hence we allow to circumvent the Yuxiang theorem. Okay, now we can kind of ignore the reference frames because it's a tensor product and we don't need them anymore. And now to finalize the decoding, we kind of undo the remaining code, which by applying the unitary U and the decoder D from the subroutine as follows. So first we apply the inverse on the physical qubits. Then we apply the decoding to get to the logical space, and now to finalize we apply UL, the unitary one more time to get back our our logical states before the encoding. Okay. In terms of the actual channel or the decoder channel, it looks like this. And again, we have the HAR, this again is the HAR measure. So let's look at the characterization of the error involved in this process. So before the encoding, we started with a logical state, rho L. After the encoding and decoding, we ended up with approximately this logical state, but again, with some little bit of error. And again, so far I haven't talked about any time of error models. So as you see, after encoding, decoding, there is a small error, and this is independent of the error models we introduced, right? So that's something to take into account. So how do we characterize this error? Well, we use the standard method. So we use the diamond norm between had we applied the unitary of interest already at the logical level without encoding and decoding, compared with first encoding, applying the unitary V at the physical level, as I said before, to the physical qubits and to the reference frame qubits, followed by decoding and seeing how well it compares. As I said before, this process so far did not include an error model, but to make it interesting, we will actually introduce the possibility of some errors via this channel C representing the error channel also in this process. And when we do so, all of this to put together, when we maximize this error over all possible unitaries we could have applied, V, right, at the logical level in SUD, after maximizing that, we get epsilon cov, which is the worst case scenario error, right, the scenario. So remember, epsilon cov will be this error. And as long as this error is small enough, then everything will be fine. Because yeah, at the end of the day, in all experimental process, there'll be some error. So as long as that there is a certain tolerance that you're happy with, we'll be fine, right? So that begs the question: how does this error scale with the number of reference frames and other parameters, right? So that's the highlight of our paper. That's the main thing, characterizing this error as a function of error models and relevant things. So let's go there. What are the error models we'll consider in this paper? So they're of the following form: some probability distribution over erasure errors on the reference frame and erasure errors on the physical qubits. So what are these local erasure errors? Well, here, for example, I've drawn one reference frame, and then erasure errors does the following: it completely erases information and throws it into the rubbish bin. So these errors have the property that they are detectable errors, and they completely, all the information is completely erased. So within the family of detectable errors, there is the worst, they are the kind of worst nightmare type of errors you can have, because when you want to, you lose all the information, not just some of it, but all of it, okay? So, okay, and these are the type of errors we will consider. Now, within this framework of erasure errors, we'll consider two sub models, if you wish. The first one we'll call the weak error model, and the one we'll discuss a bit later, we'll call the strong error model. But for now, let's start off with the weak error model. So the weak error model has the following properties. First, on the physical qubits, at least just over half of the qubits are not erased, okay? And on the reference frame qubits, at least one reference frame set of qubits are not erased. So remember, each reference frame consists of 2m qubits, right? So in terms of pictures, we can think of it like this. On the physical qubits corresponding to the original, the subroutine encoding, we have at least just over half not erased. And on the reference frame qubits, we're allowed to erase everything other than one reference frame, right? Which consists of 2m qubits. Okay, and in this particular example here of the weak error model, we will assume that the subroutine encoder and decoder can perfectly correct this type of errors. So, we encode the errors occur in the physical space, and we can decode it. This is just the identity channel, and there are many examples of potential encoder and decoder codes which satisfy this property. In the literature, for example, there's this paper by these authors from 1997. Okay, so now these are the results of our paper. The first thing is an upper bound on the error, right? And it basically, without going into the details how it depends on the dimension of the qubits involved, we'll focus on how it scales with the total number of reference frames, qubits, right, which we denoted NR, and the error goes to 0 as 1 over the total number of qubits for the reference frame squared, right, as you see here, up to higher order corrections. So this is an upper bound on the encoding error, and we also prove a lower bound on the encoding error, which is as follows. And here you see that it goes as 1 over the square of the total number of reference frames qubits, right? Or also 1 over the square of the total number of physical and reference frame qubits. So this means together the scaling is tight, right? So as I said, the optimal this method achieves the optimal scaling of 1 over the number of reference frame qubits squared, I should say, sorry, which is the same as 1 over the total number of physical and reference frame qubits squared, due to the way we've chosen the scaling. And just to say as well, this upper bound is proven under extremely general settings. Are we only taking into account the symmetry constraints for this? We only ask what is an upper bound under the covariant properties of the channels, without necessarily using reference frames, which means that this reference frame approach also is a tight approach. So out of all possible approaches, if you use reference frames, in terms of errors, you're going to do the optimal thing. Okay, so let's move on. Now let's consider the strong erasure model. So here, what we assume is that each of the physical qubits on the subroutine space can be erased, or with each qubit with some probability PE of being erased. And similarly, for the reference frame qubits, we also assume that each qubit has a probability of PE of being erased, and this probability is somewhere between 0.5. Okay. The important thing here, we call it the strong error model, because here, essentially the noise model is IID. So every individual, if you just look at one qubit and ask what is the probability of it being erased, that probability is independent of the probability of which other qubits were erased or not, right? Whereas in the other model, that's not the case, because we have this guarantee that a certain number of qubits were never erased. So that means if you look at the certain qubit and ask what is the probability of there being erasure here, it depends on what happened to the other qubits, right? Well, that's not the case here. Okay, so now in this case, the subroutine code cannot be perfect. There does not exist ones that decode perfectly, which is another indication it's stronger than the previous model, right? Because there were decoders which could decode perfectly. Nevertheless, it is known from these papers here that one can decode up to an error which vanishes exponentially quickly in the number of physical qubits. So errors can be very small. So in the particular setting, we considered, remember, N is the total number of qubits, both from the physical ones and including reference frames. So we considered the scaling where the number of physical qubits is sublinear in the total number of qubits, and the reference frame qubits is linear in the total number of qubits. We also choose their reference frame slightly differently. So before, remember, we bunched all of our NR reference frames qubits. We bunched them into 2M blocks of qubits. Now, so basically before we had not so many reference frames, but each reference frame consists of many qubits. Now we're going to divide our NR qubits differently. So we're going to have few qubits, in actually 2 qubits to be precise, per reference frame, but many more reference frames. And it turns out that this is much better in this particular case here. And really, I won't go into the reasons, but it's because we have different error models, and the saying, don't put all your eggs in the same basket, really applies here. And it's the same metaphor, which really explains why it's optimal to do this here, as opposed to the case before. Okay, so what are the scalings in this case? Well, we proved that for epsilon greater than 0, we have this upper bound in the error, which essentially scales as 1 over n. Sorry about that, some interruption. The point is that yeah, so before our upper bound was 1 over n squared, now it goes as 1 over n, and the lower bound also goes as 1 over n. So the message to take away here is that, again, the reference frame approach is tight, but if there's a stronger error model, then you necessarily have a worse scaling. It drops by a square. So it's yeah. So if you want, in some sense, you can think of the previous scales like a Heisenberg scaling, and now we have like a Shotnoy scaling, roughly speaking. That's a good way of thinking of this. And we have a worse scaling, not because of a worse protocol per se, but because we have a harsher error model. So given the error model, this is still the best thing you can do. So that's what I wanted to convey here. And now finally, in the 3 minutes that's left, I just want to point out that our encoding and decoding involved sampling of the Haar measure, which sounds very nasty because this is a very hard problem. And from a practical perspective, it would mean that our encoding and decoding could not be run because the classical computation complexity is just too much. It will take too long to perform in practice. But we're lucky because in reality, things are not so bad, because if you look carefully, these matrix elements are a polynomial of order number of physical qubits plus a half of the number of reference frame qubits plus 1 in the coefficients of U and U transpose, which means we don't actually have to sample from the Haar measure, but we only have to reproduce finitely many moments. And this is what's known as a T design, in particular unitary T design, and people have proven that these are much easier to sample from. So for example, we have this paper by these guys, which when we apply this, we approximate our encoder and decoding to an error which is this epsilon cov, which is the relevant error for this case, since we can only decode up to an error given by this number anyway. So when we do this, we find that the number of gates we need to apply to construct the approximate encoder and decoder now only scales polynomially in the total number of physical and reference frame qubits, and we have this log 1 over epsilon cov penalty as well, with for depending on how accurate we want the decoding to be. But again, we can choose this. So this at least is feasible from an experimental point of view. I should say a complexity theoretic point of view. Okay, so with that, I would just like to put up the conclusion slides, and I'll leave this here for you guys to read, and you can think about any questions you may have. And I look forward to answering your questions and seeing you online soon. So thank you very much for listening. Thanks for the organizers for organizing this conference. And also I'd like to thank once more my co-authors for being great co-authors and having this wonderful collaboration with them. So bye for now. Hope to see you soon Bye.